First of all, thank you for inviting me to this workshop. I understand that the talk that I'm giving is different from the previous talks, both in terms of application and also the methodology. But I thought in workshop on real-time decision making, it's worth mentioning the work that has been done in algorithmic questions around online advertising. I'm also thankful to Nikhil Devanur for letting me use some of his slides, and Hamid and Aroniak for pointers to the literature. So online advertising is a big and growing business. In 2015, it was around $60 billion was spent on online advertising alone. It's the dominant business model for a lot of internet companies. It helps a lot of small and big businesses thrive. A lot of the free services and content that we use on the web is essentially sponsored by online advertising. It's by now it's a very complex market with hundreds of players. Not just publishers and advertisers, other players disaggregating, aggregating the traffic, optimizing on behalf of the different players and supplying data into the system. Gives rise to very interesting problems in learning and mechanism design and optimization. It's actually an interesting area of research because by now most of these big companies have an army of engineers, data scientists, researchers, and the cycle from an idea to implementation is becoming shorter and shorter. So this is an area where you can actually have immediate impact. There is a lot of work in this area. I'm going to just focus on one specific problem, and that's sort of more the optimization aspects. And I'm going to review the work that has been done over the past 10 years and the impact of that. All right, so probably everybody here is familiar, but let me just review it quickly. How ads are typically sold. So there is a bidding by the advertisers. It's done usually beforehand, but sometimes in real time. Now an ad opportunity arrives. The ad opportunity could be somebody searching on a search engine looking for a product, or an ad opportunity could be on any other website. So I'll refer to that as a query. Then an ad should be selected and priced and then charged. And typically here, you have only a fraction of a second, maybe even in terms of milliseconds to make your decision. The allocations are related to each other because of the sort of past behavior of a specific ad or a publisher, or the information of the user, the ads that the user has clicked on before, or the previous purchases of the user. But also they are related by budget or demand constraints. So typically every advertiser has a certain budget that they want to spend over a certain period of time, a day, a week. And the real-time part of it, the decision-making, is the allocation and the pricing of the ad. And I'm going to start with a very simple model for this. Initially, we called this the AdWords problem, but probably the online budgeted ad allocation is a better name for it. Imagine you have n advertisers. Each has a budget, B1 to Bn. You have queries arriving online. When a query arrives, you can see the bids. So BIA is the bid of advertiser A for ad I. You want to allocate the query, the ad opportunity, to one of the advertisers. And here we assume that once you allocate, your revenue is going to be BIA, the bid of the advertiser for the ad. And right now, sort of simple starting point. The objective is to maximize revenue. So let me just set up the notation. So I have T queries, 1 through T, and advertisers. The BIA is the ad. The budget is B sub A. Essentially, I'm trying to optimize this objective function. The minimum of the sum of the bids of the ads allocated to the advertiser and his or her budget, summed over all advertisers. Is the problem clear? All right. So what's the simplest? What's the first algorithm one would think of? Probably, greedy is and actually that was the first thing that was implemented, is to allocate the ad opportunity to every time a query arrives, among the advertisers who have not run out of the budget, give it to the advertiser that has the highest bid. That would be the most, sort of the simplest, the myopic strategy. It's also not hard to see that the greedy algorithm does not give you the optimal solution. So here is a simple example. Imagine you have two bidders, two advertisers, and one is interested in ads, sort of about showing ads about books and CDs, and then bidder 2 is only interested in showing ads about books. Both have a budget of $100. Now imagine your situation is in such a way that initially people only query about books, so you get 100 queries about books. If your policy is greedy, what you do is that you allocate everything to bidder 1, and then when the 100 CDs arrive, the only person who is interested has run out of money, so your total revenue is going to be $100. That's not the optimum thing to do. If you had hindsight into what's going to happen, you will get 100 books to bidder 2, 100 CDs, you would get $199. So this is, what I showed you is that greedy can give you a revenue that's as bad as half of the optimum. Now it turns out that this is really the worst case example. So the competitive ratio of this algorithm, which is the ratio of the revenue over the revenue of the best offline algorithm over all sequences of the input, is at least half. So the question that we faced, and this is around 10 years ago, is that can we do better? Is a factor half the best possible ratio? And it turns out that you can do better. So you can come up with a little more clever allocation rule that penalizes the bidders that are spending their budget too quickly. So it says, instead of giving the query to the advertiser, to the bidder with the highest bid, normalize every bidder's bid by this factor of 1 minus alpha of A, where alpha is the e to the power minus unspent fraction of budget of advertiser A. So if you haven't spent much of your budget, you don't get much penalized, and then as you spend more of your budget, you get the normalizing factor in front of your bid gets closer and closer to 0, and when you run out of your budget, your bid is thrown out. Now it's a simple algorithm. The analysis is more complicated, and you can show that the competitive ratio of this algorithm is 1 minus 1 over E. That's around 0.62. You can also show that that's the best possible. So that's the, you cannot do better than that in this framework. The underlying assumption here is that the ratio of bids to budgets is small, but that's a reasonable assumption. Usually the bids are of the order of cents to dollars, and the budgets are hundreds or thousands of dollars. Any questions?
What happens when the assumption is false?
I'll get to it, yeah. All right. Now, a few comments about the model. This is there are many simplifications. I can talk for, an hour about like how many different, sort of how the reality is different from this simple model that we have considered. But the biggest ones is, first of all, we assume that we have no knowledge about the query sequence. Typically, and especially for the most popular queries, you have a lot, you can look at the day of the week, day of the month, and look at the past history and come up with an estimate of how many people are going to search for travel to Vegas today. Now, those are the most popular queries. If you look at the long tail and, the events, sort of the queries that are related to every day, sort of the news-related events, those are actually very hard to predict. But for a large fraction of them, we can actually, have a prediction. Now, I assume that we charge the bidder his or her bid. This is not what's happening in practice. Typically, there is a second price auction. So there are, what Google uses, for example, is a generalized second price auction. A number of ads are chosen, and they are, for example, showed on a search page, on the right-hand side. And essentially, the first bidder effectively pays the bid of the second, and the second highest bidder pays the bid of the third highest, and so on. Now, there are some, sort of contracts in display advertising where first price is being used, but the dominant, charging model is second price. This one is also a big deal. We are assuming that, I have changed the way I'm allocating the ads, but now the advertisers are going to respond to that. In fact, you can argue that maybe if an advertiser is using his budget very quickly, you want to let them, run out of budget because they're going to come back and add more. Now, the trouble here is that if you look at most of the advertisers actually have, fixed budget, and they don't respond very quickly to the changes in the environment. All right, so that's the starting point. I'm gonna tell you about a few, sort of follow-up works that gave us a better understanding of this problem. The first one, and this is shortly after by Bookbinder, Jane, and Nahor, was a PRIMAL-DUAL interpretation of the algorithm. So, and this is very interesting, and it's going to be very useful. So if you think about the problem, the allocation problem, you can, by and large, write it as a linear program. So you're trying to maximize your revenue subject to the amount that you're charging. Is the amount that you're extracting from every advertiser is no more than his or her budget. Every query that arrives, you can give them to at most one bidder, and XIAs are bigger than or equal to 0. You write the dual, and the complementary slackness conditions here are very similar to matching LP. So essentially, it says that every advertiser gets a dual corresponding to his or her budget that normalizes the bid of that advertiser. So think about this is the bid of the advertiser. This is 1 minus alpha of A. Alpha is the variable corresponding to the budget constraint of the advertiser, and it says, normalize the bid of the advertiser by that factor, and then give the query to the bidder with the highest normalized bid. Now, if you know the sequence of queries, you can solve this linear program. You can compute the optimum dual for every single individual, for every single bidder, and you can normalize their bids and make the allocation. In our problem, since it's an online problem, we don't know the optimum dual, and essentially we are replacing that with this function of the spent budget. So if you're spending your budget, it seems like we have to correct for your normalizing, and we adjust that. So they came up actually with a PRIMAL-DUAL algorithm that does the same thing. Now that helped in the sense that later on, Devonur and Hayes looked at the stochastic version of this problem. So they said instead of assuming that the queries are sent to us by an adversary, we don't have any information about the sequence of queries arriving, let's assume that they are generated from a distribution. So let's say they are coming from an IID distribution. Every time it's sort of a query is sampled from a distribution and sent to you, or the set of queries is fixed and we just get a random order from that set. Well, in that case, it's not hard to see that one thing that you can do is that you can wait for a certain period of time, learn the distribution, solve the linear program, learn the dual variables, compute the dual variables corresponding to every bidder, and then solve the problem. The competitive ratio here, goes to 1 as bid to budget goes to 0. So essentially it says, waste epsilon of the queries to learn what's going on and use that too. Now, if you look here, the dependence on the epsilon and on the number of advertisers is not too good. So this is not useful for practice yet, but you can do build on that idea. This idea of sort of doubling, correcting as you get more samples is used in other applications. So you make the learning a little bit smarter. You make the dependence a bit better. The nice thing about this framework is that it was later also generalized to when you have other packing constraints, not just budget constraints. Let's say in the you come up with a budget and you say you don't want to spend more than this much money total, but you say on a particular locality you don't want to spend more than 50% of your budget, or you want to have to spend your budget divided a certain way across genders or certain across demographics. So it will make your linear program more complicated, but you can solve it and you can apply the same framework.
We could think of T as not known here, the number of stages, or
the number of no, you should assume that it's known, or is known in expectation. It was also generalized later to display advertising. So in the case of display advertising, it's a little bit, the setup is a little bit different. Usually the advertisers sign a contract with the publisher, and the publisher guarantees a certain number of impressions. So, I'm going to show your ad at least, 10 million times over the next, month or so. Now, the capacity is fixed, but you're trying to maximize the value of the ads for your customer, and the value depends on the characteristics of the user. So it's a different packing problem, and a similar dual-based allocation that's can be applied here. Instead of a multiplicative normalization here, you need an additive normalization, and it's actually put in practice the same way. Later, Devonur, Jain, Shivan, and Wilkins looked at they improved the way the system learns the arrival of the queries. They call this continuous learning, and they turned into sort of the normalization, and actually you can see the formula is not very different from the sort of the original work, except that the penalty is first is the following way. First you do the calculation, you solve your LP, you collect all the information you have about the past, and you come up with a target, a spend rate for every advertiser. So you think about halfway through the day, this particular advertiser, based on my simulations, should have spent around a quarter of his or her budget. And what you do is that you come up with a actually a severe penalty function for deviating from that, and this sort of has a convergence rate that's nearly optimal. So the dependence is improved both in terms of dependence on n and also the dependence on epsilon. So this formula is what Microsoft is using for allocating its advertisement. Then there are many generalizations. For example, what happens when you have multiple ads on pages? Remember, I told you that typically you don't choose one ad, you choose a collection of ads. And once you choose the collection of ads, you know how much your revenue is because you know the bid of each person, right? So in that case, your linear program is not a simple packing. You have to write what's called a configurational linear program that looks at all these combinatorial choices. The LP is much bigger, but we also have the computational resources. We can solve that. Then there is this sort of idea of mixing worst case and a stochastic. So imagine you have some idea about the distribution of the queries. So you have some expectation of what's going to happen today. But because of external events, it starts changing. You start getting queries about a particular individual, let's say Prince dies, and now everybody is trying to buy, download songs from Prince. In that case, essentially, this deviation, these spikes, are quite valuable for the publishers. So they have to have a way of deviating from their existing, framework. We did the work, some time ago, and it's been actually generalized and used, and again, used in practice. Also, the objective function for most of these publishers is not exactly short-term revenue. They are trying to optimize the experience of the user as well. So that's where the relevance comes in, but it can be plugged into the objective function. So when it comes to implementations in practice, this is one of the few places, few areas where there is actually published result on what each specific company is using. In Google and DoubleClick, so the learning-based algorithm that I told you, briefly is the one that's being used. They also have this idea of calling optimized throttling. So this is essentially throttling is for the advertisers who are using their budget too quickly. What they do is that they optimize between a variety of parameters to slow down the rate at which an advertiser is using his budget. The PRIMAL-DUAL and control loop that I told you, that specific formula is the one that's being used by Microsoft. There are also, actually the simpler formulas are the ones that are used by, the mobile companies like AdMob and, InMobi for their native ads are using the much, sort of simpler. So the feeling that I have, sort of some is, over the past 10 years moved from a simple idea all the way to something that's being used at a scale. It's reliable. It's being used, like a technology on an everyday basis. There are still questions in about in this area of budget optimization, but they're probably better solved at the companies themselves because they have access to the data and they can run experiments. The more interesting questions are in dynamic mechanism design. After 15 years, now is actually a good time to take a look at the structure of the auctions and see whether we want to continue the generalized second price auctions, whether we actually want to run auctions for advertising, or given that how much information now the sellers have about the goods they sell, the ad opportunities, maybe they want to move to a fixed price scheme. Even in an auction, the question of how to put reserve prices, given that the market is thinning in a sense that the advertisers are the advertisers are more and more interested in a specific ads. So, like, for the user that has made a particular purchase in the past and lives in a particular zip code, and so has this long vector of attributes. Once you have queries that are like that, when you look at the number of people who are bidding on a particular opportunity like that, is smaller. So you have to find a way to put reserve prices so that your revenue does not drop. There are questions in learning, about, there are all these learning algorithms, machine learning algorithms that are running in the background, trying to figure out the characteristics of the user, of the advertiser, of the publisher, and they are interacting with selfish agents, with sort of agents that are making a lot of money, and the mixture of the sort of the learning optimization and the mechanism design, there are quite a quite a lot of interesting problems in that domain. There are surveys written. We wrote a book chapter in algorithmic game theory on the subject. There is these two, the Kurula et al. And Mehta from Google, also have plenty of interesting research problems. I'm happy to talk to you about all of them, with the caveat that I have this nagging feeling that there is enough computational and brain power dedicated to getting users to see an ad, to click on an ad, and make a purchase of something they probably don't need. A more interesting, maybe a more philosophical question is, in the context, sort of online algorithms. When you look at the adversarial nature of competitive analysis, it seems like, when you're optimizing against an adversary, and a very powerful adversary, you end up designing algorithms that are very conservative. So I really like this from the online computation and competitive analysis book. If you can see, it's the algorithm designer on a tightrope trying to balance between many options, and then the adversary is sending shock waves trying to get him off balance. Now you can think about optimizations when you have distributional assumptions. In my experience, most of the distributional assumptions are often too optimistic, and also the algorithms that you come up with depend sort of heavily, or are quite sensitive to the distributional assumptions. In this particular application, we managed to marry the insights from these different ways of modeling and come up with robust algorithms. But I still think there is a lot of dialogue that has to be done between these two ways of thinking about a problem. And sort of lastly, the problem that I'm quite interested in, that Luca asked about. So let's think about for a second the very special case of this problem, where the budgets are 1 and the bids are 0 or 1. So that's an online matching problem, all right? It's was initially studied by Karp, Vazirani, and Vazirani in this beautiful paper. They posed the problem as an online matching. Imagine you have a set of girls, and you have a set of boys arriving one by one. So the first boy arrives, and then you see which girls are interested in it. At this moment, you have to decide who to match the boy to. So let's say this person. Then the next boy arrives. Nobody's interested. The next one, between these three, you can match the boy to one of the two girls. Again, in this case, any maximal allocation. So as long as when there is you have a boy that one girl is interested in, you allocate the boy to that. You can get factor half. The work of Karp, Vazirani, and Vazirani shows that you can get the competitive ratio of 1 minus 1 over E, and that's optimum. But you can ask the question about the stochastic version. So imagine that I give you the bipartite graph, I'll give you the set of girls and boys, and tell you that from the set of boys, I'm going to sample independently every time. And there is a, I give you the probability that I sample from the set of boys, the probability that each boy is chosen, and I tell you that I'm going to sample independently. What's the optimal allocation algorithm? So now we can talk about the optimal allocation algorithm, right? This is a stochastic input. Now, it's not too hard to show that the problem is NP-hard. What's the best approximation algorithm? The best approximation ratio is unknown. There is some work in this area initially by Feldman et al. We did some work there, and the work of the BSSX, I think, is the best known approximation ratio. But for such a simple central problem, it's unfortunate that there is still such a gap between the lower and upper bound for the problem. So if I want to end with a specific, concrete problem, here it is. Thank you.
Questions?
Yes.
So, if I'm not mistaken, all the advertising results that you mentioned assume that the advertisers know precisely the utility that they're getting from each opportunity. But in reality, they're probably learning the value of opportunities from the quality of the matching results that they get over time. So, in fact, there's sort of a longer-term behavior of the system that is affected by the quality of service that each advertiser is getting. Are there any results that try to look into this?
Yes. So very true. So you can look at the problem in two ways. One is that the advertiser is trying to learn which queries, which keywords, which search engine, is giving, sort of the best result to him or to her. And you can set up actually an optimization, typically in a sort of regret minimization framework there. And there are actually quite a lot of, there are research papers, and there are also quite a lot of companies that do this on behalf of the advertiser. But another movement is, on the side of publishers, or let's say Google, or sort of search engines, is that they say instead of charging you for click, click per se does not have any value for you. We're going to charge you for the action that's profitable for you. So let's say we're going to charge you when there is an acquisition that takes place. And then, the learning can take place when the real signal, and, sort of Google can do the optimization at that. Now, there is this question of whether you want to share all this information with an already powerful search engine that may get into your business tomorrow. So depending on the context, sometimes the optimization is done at the advertiser level or at the publisher or the search engine level. Yes.
So you mentioned the point of charging for a click. So now going back to the problem formulation that you had, where you said that you're going to look at the bid for each opportunity and give it to the highest bidder. It's not just the bid, but also the probability of that ad getting clicked that needs.
Yes. Yeah. So that's another simplification. But this one is not that big a deal because you can always normalize the bid by the click-through rate.
Just multiply it.
Yeah, so it's the expected value. Yeah.
Is the strategic behavior of people in terms of choosing their budgets, is there evidence of that? Or is it just always the best strategy to update your budget as soon as your advert's shown? Or set an infinite budget?
Right. So it depends on the nature of the advertiser. So one way to think about it is that it depends on the marginal value of the additional traffic. So let's say if the additional traffic that comes to you is worth to you 50 cents per click, and you can get it with 40 cents, then why do you need a budget? Just the more the merrier. But a lot of advertisers have capacity constraints. So they, if you are a nightclub in New York City, you can only fit so many people in. If you're, selling T-shirts, you have only so many T-shirts in your system. So the budgets are usually reflecting that, the capacity constraint, there are also some organizational issues. A lot of times, the VP of marketing has a certain budget, so many $1 million a quarter, and they just want to spread it and use it over time and use it.
So effectively, I mean, one interpretation is what you're doing is effectively shaving the bids to people in order that they get the correct bid to run out their budget in the way that suits them.
No, not really, because essentially it says if you're spending your budget too quickly, I'm going to slow you down, so that your money is spent, is spread evenly over the days. So that should only help you. Yes, sir.
Could you restate your model of online stochastic matching?
Sure. So you're given a graph, a bipartite graph, and on the right-hand side for the boys, you have a probability for assigned to each node. Now, what happens is that every time I'm going to choose one boy from this set with probability proportional to the with the probability given to that person. And I'm going to do this independently, and I'm going to do this k times. And every time you get a boy a sample, you have to decide which girl you're going to assign it to.
It's done with repetition?
And it's done with repetition.
And you know the distribution?
You know the distribution. Yeah, you know the number, you know the number of samples, and you know the distribution from which you sample.
So all the girls are there from the beginning.
Yes. So the girls are there from the beginning. You also know the graph.
There are agnostic versions also where if you just know there's a distribution, but you don't know what the distribution is.
Right. Yeah. So there are agnostic versions. There are also versions in which you're going to get this set of boys, but you don't know the graph, but you just know that the set of boys are given to you in a random order. Yeah. But this is the simplest model that
What are the gaps in terms of what we know about the approximation ratio?
I think it's like it's easy to get 1 minus 1 over E. You just ignore the distribution. You can improve it to 0.79. And in terms of upper bounds, we know very little.
So the best of both worlds between worst case and stochastic nature of the problem, as well as the particular adversarial lower bound that you showed initially, kind of is reminiscent of smooth analysis. So is there any work on that line?
Yeah. For many of the applications, so a smooth analysis is actually, it's amazing. It works for, say, simplex, because it just allows you to perturb the instance slightly. And here, most of these instances, the worst case instances, are, if you perturb them slightly, still they have the same.
Thank you very much.
Thank you.